We've all seen how fast AI is moving, right? Especially these language models. They solve problems, write code, generate amazing text.
It's incredible the pace of change.
Absolutely. But here's a question, maybe a bit mind-bending. What if the next big leap isn't just making AI smarter at solving things, but turning them into, well, amazing teachers?
Teachers. Interesting angle.
Exactly. And that's what we're diving into today. There's this really groundbreaking new framework called Reinforcement Learned to Teachers, RLTs for short.
RLTs. Yeah.
And it looks like it's really changing how we train language models to be more effective educators.
So not just problem solvers, but explainers too.
Precisely. Our mission today is to unpack the key ideas from this fascinating research paper. It's called Reinforcement Learning Teachers of Test Time Scaling.
I've heard of Sakana AI. Eduardo Seaton, Tianyu Zhao, Yujin Tang.
That's the one, from Sakana AI in Japan. Yeah, they're exploring this really novel way to train LMs to be better teachers for other AIs, and maybe, just maybe, for us too.
Sounds like a fundamental shift.
It really does. And just so everyone knows, this deep dive, it's based entirely on this paper. We're going straight to the source material today, digging right into the science.
Good. Keeps it focused.
Okay then, let's unpack this. Get ready for some pretty surprising findings and maybe a new way to think about how LMs can become better teachers for us and for each other.
All right, I'm ready. Where do we start?
So let's maybe set the scene first. Think about the usual way we try to make AI better at reasoning.
Yeah.
You know, using reinforcement learning, RL.
Like DeepSeek-R1, those kinds of models?
Exactly. The goal there is typically to get the LM to solve really tough problems completely from scratch.
Right. And that hits a pretty big snag almost immediately. The paper calls it the exploration challenge.
Exploration. What does that mean in this context?
Well, traditional RL often uses what they call one-hot correctness rewards. Basically, the AI only gets a positive signal, a reward, if it solves the problem perfectly.
So it's all or nothing.
Exactly. Think about it. If you're learning something totally new and the only feedback you ever get is perfect, you nailed it, or nope, complete fail with absolutely nothing in between.
Yeah, how would you even start? You'd have no clue if you were getting warmer or colder.
Precisely. If the model can't solve it right out of the gate, at initialization, there's just no gradient, no signal telling it which direction to learn in. It's stuck.
Okay, I see.
And this leads to what's called a sparse reward problem. The useful feedback is just incredibly rare.
Like finding that needle in a haystack blindfolded.
You got it.
Yeah.
And what that often means is only the really big, already quite capable models actually show consistent improvement with this kind of RL.
Which makes it super expensive, right? And kind of exclusive.
Totally. It limits major progress to those who already have these massive pre-trained models.
Okay, so that's the exploration problem. But you mentioned it's not just about the difficulty of learning from scratch. There's something else.
Yeah, there's also this fundamental mismatch of objective.
Mismatch. How so?
Well, we train these LMs to solve problems using RL, but a really key way we actually use them is as teachers.
Right. To generate explanations, those instructive reasoning traces the paper mentions, for other, maybe smaller student LMs.
Exactly that. It's about knowledge transfer, or downstream distillation, as they call it.
So the skills needed to just get the right answer.
Aren't quite the same skills you need to explain clearly how you got that answer. Traditional RL optimizes for solving, not necessarily for effective teaching. The objectives aren't perfectly aligned.
That makes sense. Solving and explaining are definitely different skills.
And then, on top of all that, there's another practical hurdle. Training instability.
Instability, like the AI forgets things.
Sometimes, yeah, or the performance just degrades unexpectedly. Traditional RL can be quite finicky. It can sometimes lead to this output degradation.
Which sounds bad.
It is. Yeah. And that's why these training pipelines often need multiple rounds of RL. They use the outputs from one round to cold start the next one, trying to keep things on track. Yeah.
Sounds complicating. And probably adds more cost and time.
It definitely does. And one more thing, there's often this heavy reliance on what the paper calls heuristic-driven post-processing.
Okay, heuristic-driven post-processing. Break that down for us.
It basically means extra, often manual steps after the AI generates its reasoning, like using other big, sometimes closed-source models, maybe a GPT-4 variant.
To do what? Clean it up.
Yeah, exactly. To fix grammar, refactor the steps, make it look nicer, more consistent, almost like sending the AI's rough draft to an editor.
Wow. So even after all that complex RL training, You still need another AI, potentially very expensive one, to polish the output before you can actually use it effectively for teaching.
That's often the case. Adds significant cost, complexity, and sometimes introduces dependencies on models you don't control.
Okay, so exploration problems, sparse rewards, mismatched objectives, instability, and then this costly cleanup phase. It sounds like traditional RL for reasoning has some serious challenges, especially if the goal is teaching.
It definitely presents hurdles, which is why this RLT approach is so interesting.
Right, so let's get into that. Reinforcement learned teachers, RLTs. You said it's a fresh perspective. What's the core idea?
The core idea, the main intuition, is actually pretty intuitive, drawing from how we think about teaching.
Okay.
The paper puts it nicely. The ability of real-world teachers is not measured by whether they can come up on their own with complex theorems. Makes sense, right?
Yeah, my best teachers didn't necessarily discover calculus, but they could explain it brilliantly.
Exactly. What matters, the paper says, is their ability to make use of readily available solutions and devise instructive explanations for their students.
Ah, so it shifts the focus from discovery to explanation.
Precisely. That's the fundamental shift in the RLT framework. Instead of asking the LM to solve a hard problem from scratch,
You give it the answer.
you give it both the question and the solution.
Both.
Yep. The RLT's task then becomes much simpler. Just connect the dots, generate a detailed step-by-step explanation showing how you get from the question to the given solution.
Okay, that sounds way less daunting than finding the solution itself. Solves that exploration problem, presumably.
It sidesteps it beautifully. The task is much more constrained, and this is where it gets really innovative, as you said. This simpler task formulation allows them to use a dense reward objective.
Dense reward, so continuous feedback, not just pass-fail.
Exactly. No more sparse signals.
Right.
They get feedback based on how good their explanation is for teaching.
How do they measure that? How do you know if an explanation is good?
This is the clever part. They measure it by actually using the explanation. They feed the explanation generated by the RLT to a separate student model.
Okay.
And then they test how well that student understands the problem solution after seeing the RLT's explanation.
Ah, so the teacher's score depends on the student's performance. Makes sense.
Right. And the paper details two main parts, two reward terms that make up this dense reward.
What are they?
First, there's RSS. That basically measures how well the student grasps the solution itself, given the RLT's explanation. Did the explanation help the student arrive at the right final answer?
Okay, straightforward enough, like checking if the students got the answer right on a quiz after the lecture.
Kind of, yeah. But then there's the second term, RKL, and this one is really crucial.
RKL, what does that do?
It quantifies, and this is a bit technical but important, whether the think tokens themselves are interpretable logical continuations from the student's perspective as compared with the teacher's.
Whoa, okay. Think tokens. Like the AI's intermediate steps, its chain of thought.
Exactly. RKL looks at those intermediate steps in the explanation. It checks if they make logical sense to the student model. It essentially asks, does this explanation provide a coherent, step-by-step logical path?
Ah, so it prevents the teacher AI from just, repeating the solution over and over again in the explanation.
Precisely. It forces the teacher to actually explain the reasoning, the logical flow, not just state the answer or things directly related to it. It ensures the explanation is genuinely instructive.
That's clever. So RSS checks if the student gets the answer, and RKL checks if the explanation itself makes logical sense step by step.
You got it. And the overall RLT reward combines these. Plus, they add something called min-max reductions.
Min-max reductions, why?
It's to make sure the reward isn't unfairly biased by how long or short the explanation is. It ensures that every part, every token of the explanation is considered, preventing the teacher from just padding it out or making it too brief to gain the reward.
Okay, so it encourages concise but complete explanation.
That's the goal.
So putting it all together, RLTs get the question and answer, their job is to explain the steps, and they get dense feedback based on whether a student understands the answer and whether the explanation's logic is sound, regardless of length.
That's a great summary.
Theoretically, then, this should avoid the exploration problem, align the goal with teaching or distillation, and maybe even get rid of that complex, expensive post-processing step.
That's exactly what the paper hypothesizes. It sounds incredibly promising on paper.
The million-dollar question, then. Does it actually work? What do the results show?
Ah, yes, the results. This is where it gets really compelling.
Lay it on us. What do they find?
So the core finding, and this is pretty striking, the raw outputs from a relatively small 7 billion parameter RLT model.
7B. Okay, that's small compared to giants like GPT-4.
Exactly. The raw outputs from this RLT-7B model led to higher final performance on some really tough benchmark tasks, competition math like AIM, general math problems, even graduate-level science questions in GPQA.
Higher performance than what?
Higher than existing distillation methods that used processed explanations from much larger models orders of magnitude bigger, even after those explanations went through the whole post-processing cleanup routine.
Wait, really? The raw stuff from the little 7B RLT beat the polished explanations from huge models.
That's what the results in Table 1 show.
Yeah.
For instance, comparing RLT-7B trained on 17,000 examples against a baseline called Bespoke 7B, which used explanations from much larger models plus post-processing.
Yeah.
The RLT-7B achieved an overall score of 49.50, while the Bespoke 7B baseline got 46.60. The RLT was just better, straight out of the box.
That's efficiency right there.
Yeah.
A small 7B model doing better teaching than systems relying on massive models and extra steps.
It really suggests the quality of the RLT's explanations is intrinsically higher for the purpose of teaching. Kind of democratizes things, doesn't it? You don't necessarily need the absolute biggest model to create effective training data.
Definitely. Okay. What else? Does it scale? Like if you use the RLT to teach a bigger student model?
Good question. And yes, it seems to scale well, even when they use the RLT framework to distill knowledge into a larger 32 billion parameter student model.
So RLT 32B.
Right. It still outperformed all the prior methods they compared against. Looking at the Table 1 again, RLT 32B hit 73.23 overall, while the Bespoke 32B baseline was at 71.47.
So the teaching method holds up even when the student is more capable.
It does. It suggests the quality of the explanations generated by the RLT framework remains superior.
Okay, impressive performance. What about that instability issue with traditional RL? Did RLTs help there?
They looked at that too, specifically at using RLT-generated explanations for cold starting traditional RL.
Cold starting. Like giving the traditional RL a better starting point.
Exactly. And the results were significant. Table 2 shows that using the RLT-7B explanations to kickstart traditional RL training led to a final score of 50.53. This was substantially better than other cold start methods, even ones that used explanations post-processed by GPT models, which only reached 43.93.
So RLTs not only teach students well directly, but they also provide a much better foundation for further RL training. That tackles the instability and slow start problems.
It seems to, yeah. It provides a much stronger, more effective starting point.
Anything else that stood out in the results?
One more really interesting finding. Out-of-domain zero-shot transfer.
Okay, what does that mean?
They took the RLT, which remember was trained primarily on math and science problems.
Right.
And they tested its ability to generate useful explanations for a completely different kind of task, something called the countdown task. It's like a number game. They did this without any specific RL retraining for countdown.
So just applying the math science teacher to a number game. How did it do?
Amazingly well. Using the RLT's explanations for distillation on the countdown task achieved a performance score of 66.5. That was significantly higher than trying to train a model on the countdown task using direct RL from scratch, which only got 50.8.
Get out. So the RLT, trained on one domain, could effectively teach in a new domain better than direct training.
That's what Figure 4 in the paper suggests. It speaks volumes about how reusable and perhaps how fundamental the explanatory skills learned by the RLT are.
Wow. Okay, these results are genuinely compelling. Higher performance with smaller models, better scaling, better cold starting for RL, and strong transfer to new domains.
Yeah, it really paints a picture of RLTs being potentially much more efficient and versatile.
As the paper puts it, overcoming the large costs of RL by focusing on these stronger, smaller, and highly reusable specialized teachers.
That sums it up nicely.
So, we see that it works, and works surprisingly well, but how? What is it about that dense reward function, that RSS and RKL combination that makes such a difference? What's the secret sauce here?
Right. Understanding the why is crucial. The paper dives into this analysis as well. First off, they found a really clear correlation between the RLT reward score and explanation gets and how effective that explanation actually is for teaching the student model.
So the reward function is measuring the right thing.
It seems so. They reported a Pearson correlation coefficient over 0.89.
Which is very high, right?
Yeah.
And so reward score is a really good predictor of teaching success.
Exactly. A coefficient that high indicates a very strong positive relationship. It validates that the reward they designed is indeed capturing the essence of a good explanation, at least from the student model's perspective.
Okay, so the reward works. But what do the explanations themselves look like? How are they different from, say, the traces generated by traditional RL methods like R1?
That's where the qualitative analysis comes in, looking at examples. And the differences are quite noticeable. RLT explanations are described as being much more grounded.
Grounded, meaning?
More focused on clear, logical steps connecting the problem to the solution. And interestingly, they found RLTs sometimes even managed to add new verification steps not considered by R1.
So the RLT is not just explaining the path, it's sometimes double-checking its work along the way.
Kind of, yeah. Adding extra checks for correctness or clarity. In contrast, those traditional R1 traces sometimes rely on external tools like calling a calculator or use idiosyncratic language patterns that might be efficient for the model itself but aren't ideal for teaching someone else.
So RLTs produce cleaner, more self-contained, and potentially more rigorous explanations, like a really meticulous tutor.
That seems to be the case based on the examples in figures 5, 9, and 10 of the paper.
Okay, that makes sense. Now, you mentioned those ablation studies earlier where they remove parts of the system to see what happens. What did they reveal about the reward function?
Those were really insightful. They really highlighted the importance of each component, especially that RKL term.
Right, the one about logical steps. What happened when they took RKL out?
Without RKL, the teacher model basically lost the ability to tell the difference between an explanation that genuinely guides the student step by step and one that just, well, makes the final solution seem more likely without a clear path.
So it couldn't distinguish good teaching from just hinting strongly at the answer.
Pretty much. And what happened was the teachers started to exploit the repetition tendency common in language models. It often just ended up repeating tokens from the solution itself within the explanation.
Oh, so it cheated, basically. It didn't explain. It just parroted the answer.
Effectively, yes. And the result. The average length of the explanations dropped dramatically, and more importantly, the student's final performance plummeted.
Wow. So that RKL term, focusing on the logical flow of the think tokens, is absolutely critical for forcing the RLT to be a real teacher.
Absolutely critical. Table 9 and Figure 11 really drive that point home. It validates why that specific reward component is so vital.
Okay, what about the other part they tested removing? Those min-max reductions. The thing that prevents bias based on explanation lengths.
Right. When they removed those, the rewards did become biased by length.
Yeah.
And the teacher responded exactly as you'd expect.
Let me guess. It started writing super long explanations.
Bingo. It produced overly long explanations filled with many additional unnecessary steps that are just semantical repetitions of each other.
Like a student trying to hit a word count on an essay by repeating the same point in different ways.
Precisely. Now, the paper notes the performance drop here was more moderate compared to removing RKL. The student could still learn, just less efficiently.
But it still hurts training efficiency and probably makes the explanations harder to follow, right?
Definitely. It negatively impacts both training time and the efficiency of generating explanations later. Figure 12 shows examples of this repetitive padding.
So it really is a delicate balance then.
Mm-hmm.
You need the RSS for the outcome, the RKL for the logical process, and the min-max reductions to keep the explanation focused and efficient. Each piece is doing important work.
Exactly. Each part of that carefully crafted reward function plays a crucial role in shaping the RLT into an effective, efficient teacher. It's not just about the answer, it's about the way you explain it.
Fascinating stuff. So looking beyond the technical details, what's the bigger picture here? What's the potential broader impact of RLTs?
Well, I think the most significant impact is how RLTs enable smaller LMs to generate much better synthetic data for distillation.
Creating high-quality training examples for other models?
Exactly. Before, generating really good reasoning data often required access to those prohibitively large and closed-source LMs we talked about. RLTs seem to offer a way for smaller, more accessible models, like a 7B parameter model, to create top-tier teaching material.
So it lowers the barrier to entry for training really capable reasoning models. It democratizes it.
That's the potential, yes.
Huh.
It could make advanced AI training techniques much more accessible to a wider community of researchers, startups, and developers who don't have massive computational resources or access to proprietary models.
That's huge. Of course, no research is ever completely finished. The paper itself must mention limitations or areas they didn't explore yet, right? We should probably touch on those for a balanced view.
Absolutely. and they're quite upfront about it. One key limitation is that RLTs in their current form rely on having access to the ground truth solutions.
Ah, right. The teacher needs the answer key before it can explain it.
Correct. So it works well for problems where solutions are known or can be easily verified, like math, but maybe less directly applicable where ground truth is ambiguous or unavailable.
Makes sense. What else?
The current training process also involves an initial supervised fine-tuning phase. They start by training the RLT on some pre-collected reasoning examples before the reinforcement learning kicks in.
So it needs some existing examples to get started.
Yes, it's not trained purely from RL from scratch. Also, the framework uses that additional student model for computing the rewards.
Right. The teacher's score depends on how a separate student model does.
Yeah, although the paper mentions this seemed to have minimal downsides in their experiments, it is an extra component in the system.
Okay. Any other unexplored avenues?
They mentioned they didn't explore having the same model act as both teacher and student, maybe alternating roles, or training them concurrently.
Like a self-teaching loop.
Potentially, yeah. That wasn't part of the study. There were also, naturally, computational constraints. They mainly focused on those small, inexpensive 7B models.
Understandable.
And they had a maximum context size limit during the RL and distillation phases, 16,384 tokens. Plus, they didn't systematically explore using a much larger or broader set of initial question-solution pairs to train the RLT.
Okay, so still plenty of room for future work, refining the process, scaling it up, applying it to problems without clear solutions.
Yeah, definitely. And the paper points towards some really exciting future directions based on this work.
Such as?
While that idea of the same model could even take both roles is very intriguing, could we unify this RL-based teaching with supervised learning in one model?
A model that learns to solve and teach simultaneously.
Perhaps. And they also mentioned the possibility of creating online curricula tailored to the students' specific learning dynamics.
Whoa! So the RLT teacher could adapt its explanations in real time based on how well a particular student model is understanding things.
That's the vision. A truly adaptive AI tutor for other AIs. Imagine how that could accelerate learning.
That's the pretty profound idea. Personalized education, but for AI.
It opens up fascinating possibilities.
So wrapping things up, it feels like RLTs, despite the current limitations and open questions, represent a really significant step. A move towards more accessible, more efficient AI development.
I think so. It shifts the heavy lifting, the burden of expensive and sometimes unstable RL towards creating these smaller, specialized, and highly effective teacher models.
It's less about brute force solving and more about elegant, efficient knowledge transfer.
Well put.
So what we've really deep dived into today is how this shift in perspective training LMs, not just to solve, but to explain things we already know the answer to, can unlock surprising levels of efficiency and capability.
A simple shift with potentially large consequences.
It makes you wonder, doesn't it? Imagine a future where AI models aren't just problem solvers, but they're becoming these self-improving educators, continuously getting better at explaining complex ideas, teaching other AIs, maybe even teaching us more effectively.
What new kinds of breakthroughs could that kind of accelerated AI-driven learning and discovery unlock? It's a powerful thought.
It really is. So for everyone listening, what stands out to you from this deep dive into reinforcement learned teachers? What possibilities does this spark in your mind? Definitely something to mull over.